Let X be a column random vector consisting of n random variables, x1, x2 up to xn. We adopt the convention that a bold-faced letter represents an n-dimensional column vector. The covariance matrix of the random vector X, denoted by K sub X, is defined as the expectation of X minus expectation of X, which is a column n vector, times the transpose of itself, which is a row n vector, and so this is actually an n by n matrix. We are going to show that the ijth element of this n by n matrix is equal to the covariance of xi and xj. Note that the ith diagonal element, namely covariance of xi and xi, is equal to the variance of xi. The proof is elementary. First, consider the product of x minus expectation of x and the transpose of itself. Then the ijth element of this n by n matrix is equal to xi minus expectation of xi times xj minus expectation of xj. Then we take the expectation inside the matrix to see that the ijth element is actually equal to the covariance of xi and xj. In a similar fashion, we define the correlation matrix K tilde of the random vector X as the expectation of X and X transpose. This is an n by n matrix with the ijth element equal to the expectation of xi times xj. The covariance matrix and the correlation matrix can be related in two ways. First, kx is equal to k tilde x minus expectation of x times the transpose of expectation of x. Second, the covariance matrix kx is equal to the correlation matrix k tilde of the random vector x minus expectation of x. These two relations are actually vector generalizations of the following two relations. Specifically, this is a generalization of this, and this is a generalization of this. We now define the Gaussian distribution, which will be used repeatedly in this chapter and the next chapter. The Gaussian distribution of a real random variable with mean mu and variance sigma square is denoted by n of mu comma sigma square, with the probability density function fx equals 1 over square root 2 pi sigma square e to the power minus x minus mu square divided by 2 sigma square for all values of x. The multivariate Gaussian distribution of an n-dimensional random vector with mean mu, where mu is an n-dimensional vector, and covariance matrix K, is denoted by n of mu comma k. The joint PDF of the distribution is given by fx equals 1 over square root 2 pi to the power n times the square root of the determinant of the covariance matrix K times e to the power minus 1/2 x minus mu transpose times k inverse times x minus mu for all k-dimensional vectors x, where the covariance matrix K is a symmetric positive definite matrix. Note that x minus mu transpose is a 1 by n vector, K inverse is an n by n matrix, and x minus mu is an n by 1 vector. And so the product of these three matrices is a scalar. We have already set up the notations for random vectors. In section 10.1, we will discuss some basic operations on a random vector. A square matrix K is symmetric if K transpose is equal to K. That is, by taking the transpose of the matrix remains unchanged. An n by n matrix K is positive definite if X transpose times K times X is strictly positive for all non-zero column n vector X, and is positive semi-definite if X transpose times K times X is greater than or equal to 0 for all column n vector X. Proposition 10.3 says that a covariance matrix is both symmetric and positive semi-definite. We will leave the proof as an exercise. We now discuss a very important property of symmetric matrices called diagonalization. A symmetric matrix K can be diagonalized as K equals Q lambda Q transpose, where lambda is a diagonal matrix and Q, also Q transpose, is an orthogonal matrix. That is, Q inverse is equal to Q transpose. The proof of this fact is elementary. Let Qi be the ith column of the matrix Q. Because Qi form a set of orthonormal bases, Qi times Qj transpose, that is, the dot product of Qi and Qj, is equal to 1 if I is equal to j, and is equal to 0 if I is not equal to j. Now consider the product Q times Q transpose, where Q consists of the columns Q1, Q2 up to Qn, and Q transpose consists of the rows Q1 transpose, Q2 transpose up to Qn transpose. By regarding Q as a row vector and Q transpose as a column vector, we see that the ijth element of Q transpose is equal to Qi times Qj transpose. Because the matrix Q is orthogonal, we see immediately that Q transpose is equal to the identity matrix. And from this, we see that Q inverse is equal to Q transpose. Another property is that the determinant of Q and also the determinant of Q transpose is either equal to 1 or minus 1. Consider the square of the determinant of Q. Because the determinant of Q is equal to the determinant of the transpose of Q, this can be written as the determinant of Q times the determinant of Q transpose. This can be further written as the determinant of Q times Q transpose, which is equal to the identity matrix, because Q transpose is equal to Q inverse, as we have shown. Now the determinant of the identity matrix is equal to 1, and so we have the square of the determinant of Q is equal to 1. And this shows that the determinant of Q and the determinant of Q transpose are equal, and they are equal to either plus 1 or minus 1. Let lambda I be the ith diagonal element of the matrix lambda, and Qi be the ith column of the matrix Q. Then KQ is equal to Q times lambda times Q transpose times Q. By the associativity of matrix multiplication, we have Q lambda bracket Q transpose times Q, where Q transpose times Q is equal to the identity matrix. And so we have shown that KQ is equal to Q lambda, or K times Qi is equal to lambda I times Qi, which we now show. Consider KQ, where Q consists of the columns Q1 up to Qn. Upon multiplying K into the matrix, we obtain the columns KQ1, KQ2 up to KQn. On the other hand, consider Q times lambda, where Q consists of the columns Q1, Q2 up to Qn, and lambda consists of the diagonal elements lambda 1, lambda 2 up to lambda n. We then obtain the columns lambda 1, Q1, lambda 2, Q2, all the way to lambda n, Qn. Upon equating the columns of Kq and Q lambda, we see that Kq1 is equal to lambda 1 Q1, so on and so forth, or Kqi is equal to lambda I times Qi for all I. That is, Qi is an eigenvector of K with eigenvalue lambda I. Proposition 10.4 says that the eigenvalues of a positive semi-definite matrix are non-negative. Consider eigenvector Q, which is non-zero, and the corresponding eigenvalue lambda of a positive semi-definite matrix K. That is, Kq is equal to lambda Q. Since K is positive semi-definite, Q transpose times K times Q is greater than or equal to 0. Now Kq is equal to lambda Q from the above, and this is equal to lambda times Q transpose times Q. Now Q transpose times Q is the magnitude square of the vector Q, and so it is strictly positive, and therefore we see that lambda is greater than or equal to 0. This proves the proposition. As a remark, since a covariance matrix is both symmetric and positive semi-definite, it is diagonalizable and its eigenvalues are non-negative. Proposition 10.5 is about taking linear transformation of a random vector. Let y equals A times x, where A is an n by n constant matrix. Then K sub y, that is, the covariance matrix of y, is equal to A times K sub x times A transpose. And similarly, K tilde sub y, the correlation matrix of y, is equal to A times K tilde sub x times A transpose. This proposition is proved as follows. Consider K sub y equals expectation of y times y transpose minus expectation of y times the transpose of expectation of y. To obtain the next line, we only have to note that y transpose is equal to x transpose times A. Now AX times x transpose A is equal to A times x transpose times A transpose. For the second term, by the linearity of the expectation operator, we can move it inside the matrix A. And similarly, we can move this expectation inside the matrix A transpose. Now for the first term, again, by the linearity of expectation, we can move it inside the matrix A and A transpose. Then by factorizing the matrix A and factorizing the matrix A transpose, we obtain A times the square bracket times A transpose. Now inside the square bracket, we have expectation of x times x transpose minus the expectation of x times the transpose of the expectation of x, which is K sub x, the covariance matrix of the vector x. This proves the first part of the proposition. The proof for the second part of the proposition is similar, and it is omitted. The next proposition is about the correlation of a random vector. Let y be Q transpose x, where the matrix Q is obtained from the diagonalization of the matrix K sub x. That is, Kx is equal to Q times lambda times Q transpose. Then K sub y is equal to lambda. That is, the random variables in y are uncorrelated, and the variance of yi is equal to lambda I for all I. We now prove the lemma. By proposition 10.5, K sub y is equal to Q transpose times K sub x times Q, because y is equal to Q transpose times x. Now, by the diagonalization of K sub x, it can be written as Q times lambda times Q transpose. And so, we have Q transpose times Q, that is the identity matrix, times lambda times Q transpose times Q, which again is the identity matrix. So we obtain K sub y is equal to lambda. Since K sub y is equal to lambda, which is a diagonal matrix, the random variables in y are uncorrelated because covariance of yi and yj is equal to 0 for all I not equal to j. Furthermore, the variance of yi is given by the ith diagonal element of K sub y equals lambda, that is lambda I, and so the proposition is proved. The next corollary says that any random vector x can be written as a linear transformation of an uncorrelated vector. Specifically, x can be written as q times y, where kx is equal to q times lambda times q transpose. The proof is straightforward. In proposition 10.6, y equals q transpose x implies qy is equal to q times q transpose times x, where q times q transpose is equal to the identity matrix, and so we have x equals q times y. Proposition 10.8 says the following. Let x and z be independent, and y is equal to x plus z. Then the covariance matrix of y is equal to the covariance matrix of x plus the covariance matrix of z. Here are some remarks. If y is equal to summation xi, I from 1 up to n, where x1, x2 up to xn are mutually independent, then the covariance matrix of y is equal to the sum of the covariance matrices of xi, where I is from 1 up to n. When xi are scalars, this reduces to variance of y is equal to summation variance xi, I from 1 up to n. Proposition 10.9 is about preservation of energy for an orthogonal transformation. Let y equals q times x, where q is an orthogonal matrix. Then the expectation of summation yi square is equal to the expectation of summation xi square. We now prove the proposition. Consider summation yi square equals y transpose times y. Now y is equal to q times x. And so y transpose is equal to x transpose times q transpose. Then we have x transpose times q transpose times q times x, where q transpose times q is equal to the identity matrix. And so we have x transpose times x, which is equal to summation xi square. Then the proposition is proved upon taking expectation on both sides.